And we're back. Welcome back from the weekend. Today we will talk primarily about calculating confidence intervals. This module, this setting rather, will be relatively light and we'll focus primarily on MATLAB, and then we'll finish up the balance of this module on Thursday. And so a little bit of the administrative bits, the reading for confidence intervals, both what they are as well as how to calculate them, are section 9.2 up through 9.2.1, including 9.2.1. It's only 2 pages. I know what a 2 pages it is. Please make sure you are doing that reading. You might find you need to consult some outside sources. That's perfectly fine. Written exam number 2 will be a take-home exam, a 24-hour take-home. It will auto-release to start at 9:30 on the 21st of April, which is Tuesday, during that class period. And I will take that time to be online during the class period. I'll start the usual live WebEx session, and it's an opportunity for you to ask questions about the take-home exam. Now, certain questions I can't answer and certain questions I can answer, and this is your opportunity to use that class as an opportunity to get those questions answered. So I'll just bring up WebEx, and I will be online with a blank slate, PowerPoint, and I will answer questions and draw things on the whiteboard and all that good stuff. So please mark your calendars. All the material, including max likelihood, method of moments estimation, stuff about confidence intervals is fair game, and we also talked about classification, and we had that classification assignment, project assignment. So this written exam is to be an individual effort. And for part of that, you'll be signing and submitting an honesty statement. And so I'm quite strict about that part. It's an individual effort. And so you can't collaborate with someone on this. You should treat it as if it were a regular exam. It's certainly something you can get done in 24 hours. And if there are assignments, or rather, if there are exams submitted that have the same solutions, all parties will receive a 0. So please take that to heart. All right. So with that, let's pick back up where we left off. We talked about confidence intervals, and we said a confidence interval is an is an interval that is a so-called 1 minus alpha times 100. You read that as a percentage. A 1 minus alpha times 100% confidence interval for some unknown parameter theta. If it contains that parameter theta, that interval AB contains that parameter theta with some probability, namely 1 minus alpha probability. And so the example we gave, if alpha is 0.05, we refer to that as a 1 minus 0.05, which is 0.95, multiplied by 100, that it would be a 95% confident interval. And so effectively, that talks about this idea of a covering probability. With probability of 95%, theta, your unknown ground truth parameter, will have values that fall within that interval. Said differently, you could say that interval AB covers theta. So we also talked about this idea of repeated set of samples from a Poisson distribution. At time t0, we take n many samples. That's the first row. At time t1, we take another n many samples, and up to and including a number of rounds, the mth round, time tm, we take also n many samples. Now, from each window or set of samples, we calculate our lambda hat, our estimator, that's going to stand in place for lambda. And so because from one round to the next, our n many samples can vary, they're different because this is stochastic, so too will this lambda hat be different. And so this set of lambda hats that we get over those m many intervals, those form a distribution, and that distribution, as we had discussed, is the sampling distribution for lambda hat. Now, certainly the standard deviation of the sampling distribution is the standard error for this estimator lambda hat. Moreover, the mean, if we do this right, we have enough samples over enough rounds, is going to be the ideal unknown ground truth parameter lambda. But as we discussed, lurking around somewhere within the sampling distribution is the ground truth value of theta. And so the population parameter lambda is not random. It's a constant, but you don't know what it is. And so because this interval AB is stochastic, the associated probability when it comes to confidence intervals is this idea that this interval AB covers or includes theta's ground truth non-random or constant value. And so this idea is captured by this figure, and this is figure 9.2 from the book, and it talks about this idea of a coverage probability. And so for each set of lambda, you have an associated, or lambda hat, you have an associated confidence interval. The lower end here is A, and the upper end is B, and here's our ground truth theta, which is unknown. It's constant. Now you notice we get a different confidence interval from one round to the next, just like we had from the previous diagram or previous slide. And the idea of a 95% confidence interval means that 95% of these different intervals AB will include or cover theta. So that's what 95% confidence interval means. And so we didn't discuss in this, what we didn't discuss is how you calculate this confidence interval. So let me select the blue pen color, and that's going to be the subject of today. And we're only going to stop at a demonstration with MATLAB leading up to that. Okay, so let's look at how you construct confidence intervals. So let's say you have a sample, x1, x2, x3, up to including xn. So you have n many samples, and you want to have a confidence level of 1 minus alpha. So if alpha is 0.05, this would be a 95% confidence interval. And so the idea then is, how do you construct this confidence interval AB? Well, this confidence interval, if it's a 95% or 1 minus alpha confidence interval, that means that there's going to be this interval AB such that the total probability associated with it is going to be 1 minus alpha. So if we're talking about a 95% confidence interval, that means if you were to sum up all the probability mass or integrate all the probability mass between the endpoints A and B, well, that would be 0.95. So that's what we're after here. And so you have an unbiased estimator, theta hat, and this unbiased estimator is going to stand in place for this unknown ground truth parameter theta. And so let's assume that this estimator theta hat has a normal distribution. That's really, really important to this construction. As a normal distribution, you can certainly standardize it. And what does that mean to standardize a normal distribution? Well, let's say you want to examine data, and this data is governed by different distributions. On the left-hand side, we have the Poisson distribution, and on the right, if lambda equals 3. And on the right-hand side, we have the exponential distribution with lambda equals 3. Now, of course, a Poisson is a discrete distribution, and exponential is a continuous or real valued distribution. So for Poisson, you're going to sum probability mass using summation. For exponential, you're going to use integration. Okay, so these are certainly different distributions. Now, you have data, and data is governed by these two different distributions. So you're going to have samples you produce from the Poisson and samples you produce from the exponential. Now, in order to compare these two samples together, you can't make an effective comparison. You're comparing two different things. And so Poisson talks about the number of people that arrive in windows of time or events that occur in windows of time, such as the coffee shop. And the exponential deals with the time between events. Right? So they're two different things. So how would you compare the variability of these? How would you compare how compact or how densely distributed these two distributions are to one another? You can't, because it's an apples to oranges comparison. They're just two different quantities. So what you can do is you can make use of the central limit theorem. We talked about that last semester in stochastic computing, and you can make them both into normal distributions using the central limit theorem. And how do you do that? Well, you take all these samples and you add them together. When you have statistics that involve a summation in the calculation of that statistic, well, that summation adheres to and is governed by the central limit theorem. Okay, so let's call S sub n, let's call that our sum. And that is a typo. Let me take my pen here. That should be an X sub n and not an S sub n. So let me just write in an X. So we have n many samples. X1 is the first sample. We have an X2, X3, X4, and this is the nth sample, X sub n. Okay, so we're just going to abbreviate that as S sub n. Okay, so if you were to take the expectation of S sub n, That's the expectation of x1 summed together, all the n many x's. Now, expectation adheres to the property of linearity. That means if I take the expectation of the sum, that's the same as the sum of all the expectations. And by that, I mean the expectation of x1 plus dot 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 xn, that's just equal to the expectation of x1 plus dot 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 the expectation of xn. Now, of course, we know from before that the expectation of variables, just mu, it's mean. So we're adding mu to itself plus dot 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 mu. We're adding mu to itself n many times. And so that's n times mu. Likewise, with the variance, it's something similar. Well, the variance of S sub n is the same as the variance of x1 plus dot 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 xn. Now, variance exhibits the linearity property. That's the same as the variance of the individual samples, variance of x1 plus dot 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 variance of xn. Okay, and we know from before, well, the variance of a variable is just sigma squared. So we're adding up these sigma squares with one another n many times. All right, so that's just n times sigma squared. So now we have the expectation of the sum of samples of a random variable, and we also have the variance of the sum for this random variable. Okay, so this essentially is a normal distribution in its shape. It's a normal, but the normal for this Sn is going to have a different mean and a different variance. The mean of the sum is the expectation, n times mu, and the variance is just going to be n times sigma squared. Right? So let's try this out in MATLAB, and essentially in doing this, you can take your samples, add them together, and the distribution of the sum, that statistic, which is the sum of samples, is going to have a normal distribution. And in doing that, you can make any distribution, regardless of whether it's a Poisson, whether it's an exponential, whether it's a geometric, or what have you. You can make any distribution look like a normal by just taking a bunch of samples from it, adding them together over some number of rounds. So let's try this out in MATLAB and see what happens. And we're going to do this with the exponential distribution, and we'll do this also with the Poisson distribution and see how that plays out in reality. Well, let's bring up MATLAB, and we're going to start a new script. And let's just save this. And let's call this Make Normal 2020. Okay. So we're going to start out, and then we're going to have some number of samples, num samples, and that's going to be the number of samples from our distribution. So let's say 100 samples. Okay, so now we're going to have a Poisson distribution, so its parameter is going to be lambda. And let's say, for the sake of argument, lambda was, I don't know, 7. Okay, lambda is 7. And then our exponential distribution, lambda, let's call that lambda p for Poisson, and lambda e for exponential. And let's say lambda for exponential was, I don't know, 12.4. Okay. So we have two different distributions, and now let's make a number of samples. So Poised samples equals, and let's say Poised R&D. Let me make sure I have the right API. Poised R&D. Okay, Poised R&D lambda p from the Poisson with parameter lambda equals 7, the ground truth population parameter. And I'm going to make one by, let's num samples many samples, and then exponential samples is exp R&D lambda. Let's make sure, again, help exp R&D, and exp R&D lambda E 1 by num samples. Okay, so if we plot a figure, let's say subplot, we're going to plot them side by side. Subplot, and let's make 1 by 2 subplot. Subplot 1 by 2, 1 row, 2 columns. The first one, that's going to be the Poisson. Let's see, histogram, poise samples, num bins. Let's give it number of bins let's call it 20. Num bins is 20. We're going to give them both the same number of bins for the histogram. And so we have number of bins, 20. I don't think it likes histogram. Help hist, probably histogram and not histogram. Use histogram. Okay, histogram. Poise samples, and let's subplot 1, 2, 2, and it's a histogram, exp samples num bins. Okay, so if we do that, save, and I just like the display done at the end, so I have an executable line on which I can set a breakpoint. So let me save that, and now I'm going to run it, set my breakpoint, I'm going to run that, and you will see the figure. And in this figure, you're going to see the Poisson on the left and the exponential on the right. Now, that's not a lot of filled-in gaps. So let me bump up the number of samples, let's say to 200, and let's see how that looks. Or we could decrease the bin count. Nonetheless, we can see there it looks a little bit better. So let's make that 400. Okay, so quit debugging, save, and let's run that, and we should get a nice shape here. Maybe 20 bins might be a little aggressive. Let's say 500. Let's bump the bins down to 15, and let's keep that at around 400 samples. Okay, so let's try that out. So we get a nice Poisson shape here, and we get a nice exponential shape. Okay. If we try going back to 20, let me see what looks good. Let me double that to 800 samples, and we're just going to make sure that we get a decent. Okay, so if we see that, I kind of don't like that Poisson distribution. So if I bump that down to 15, let's see if we can get something that looks a little bit more continuous for the Poisson. Let's see, save, run. There we go. So there we go. There's a Poisson. Let's see if we can eat away at some of these. Let's make that 600, just so that we have a little bit faster computation by decreasing the number of samples. There we go. All right. So let's say 600. That's good enough. So here we have a Poisson, and here we have an exponential on the right. So I'm going to bump that back to 800. I liked how it looked before. So let me save that. Let me run it. And so now, great. So this is a Poisson, and this is your exponential. You notice they're not normal distribution. This Poisson is certainly not symmetric. The exponential is certainly not symmetric. And moreover, they're very different from one another. Okay, so now let's do this. Let's now take that same num samples 800, and now we're going to sample from over a number of rounds, that 800 many samples, and we're going to sum them together, and then we compute the distribution of that statistic called the sum. So Poisson, so let's say number of trials, and how many times we're going to do this. Let's say we're going to do that 500 times. So 500 times, we're going to sample 800 samples from Poisson, 800 samples from an exponential. Okay, so let's try this out. For I goes from 1, increment by 1, up to num trials. And, okay, what am I going to do? I'm going to save off that sum is. So Poisson samples, Poisson sums is equal to zeros 1 by num trials. Okay, so I need a place to store those sums. And I'm going to say exp sums, sum of those exponential variables, random variables that I sample, zeros, 1 by num trials. Okay, so now num trials many times, I'm going to say t samples equals poised R&D lambda p 1 by num samples. So I'm taking num samples many Poisson from the Poisson. E samples equals exp R&D lambda e 1 by num samples. Okay, so I'm going to take num samples many samples. I'm going to do that num trials many times, 500 times. So then I say T sum is equal to sum P samples. That's the sum. Okay. E sum is equal to sum of E samples. Okay. P sum and E sum. There we go. So those are the sums, and now I'm going to save them. Poised sums 1 comma I is equal to P sum, and then E sum 1 comma I is equal to E sum. Okay, so now I'm going to look at the shape of these two distributions. I'm going to plot a histogram when I'm done with all this. So let me reuse all of this subplot, and I'm going to rename that figure figure 2. And I'm going to do the subplot instead using poised sums, and using E sums. And I have a typo here. That should be E sums, not E sum. So, okay. So now I do that, and I'll compare figure 1 and figure 2. And so here, let me have my breakpoint. Okay, save, and let me run this. Now it's going to take a little bit of time because I'm doing a lot of sums. Oh, that was pretty quick. All right. So here on the left-hand side, figure 1, draw your attention there. Here on the left-hand pane of figure 1, I have my Poisson distribution. Then on the right-hand part of figure 1, I have my exponential. Now here, figure 2, these are the sums of those 800 many samples from the Poisson. That looks like a normal. And also looking like a normal is that sum of the 800 many samples from the exponential. So now, certainly you'll notice here, the peak is pretty high, right? The value here is 93, and I get a lot of those samples, right? And so here, 5,600 is the sum, and 93 times I get a sum of 5,600, for example. So as you can see here, it doesn't matter what the original distribution is. If I compute some quantity that contains a sum in it, some statistic that contains a sum, includes a sum, that result by central limit theorem is normal in its shape. You can see this is Poisson, it was converted to a normal. This is exponential, it was converted to a normal by summing. Now, of course, let's try something else. Instead of just the sum, let me divide the sum by the number of examples, right? So here I have the sum, and instead of the sum, I'm going to compute the mean, right? So sum over num samples, right? Sum over num samples. So now we're going to have still this normal shape because the mean, or the sample mean, x bar, it involves the sum. It's the sum of all the examples divided by the number of examples you have. So let me save that and let me run it. And there's figure 2. You notice here it's a little bit lopsided, but if we had enough samples, certainly you'd see that it is in fact normal. So let's try that out, test that assertion. Num trials is 500. So what if we said, instead of 500 trials, let's say 2,000 trials. We bumped it up by 4 times as much. All right, so the trials has more examples of what this thing is. Then you notice here, guess what? So figure 1, there's my Poisson, there's my exponential. Those are the raw distributions I started with. And now from repeated sampling, computing the mean, this is the mean of the Poisson samples. That's the sampling distribution. And this is a sampling distribution for the exponentials, and they both look normal. In fact, they look very close to one another. Not exactly, but they're close enough. But they're certainly both normal. Okay, and so with that, I will certainly post this on the Blackboard alongside the module for lecture 17 concerning constructing confidence intervals. So let's go back and pick back up. And so we try this in MATLAB, and regardless of what the distribution is, you can make it look like a normal distribution simply if your statistic involves a sum. And the central limit theorem is what allows us to do this. Okay, so we will end there, and we will pick back up on Thursday. I will see you online Thursday. Take care.